So I'm a professor at the University of Chicago in the Department of Astronomy and Astrophysics, and part of my job there is teaching courses. Most of these courses are in things like cosmology and high-energy astrophysics, intro astronomy courses, and other stuff like that. But this quarter, I'm teaching something very different, a course that I've developed called Philosophical Problems in Cosmology. This course lies somewhere in the intersection of science, philosophy, and history. And in today's episode of the podcast, we're going to talk about some of the stuff that I've been talking with my students about in this class. In particular, I'm going to ask the question of what we're really doing when we go about doing science. And why does science seem to work so well?
And I want to add before we get started that we seem to be in this political moment where there's just this very large distrust of science. But in today's episode, we are just going to take for granted that science works. We won't be asking, does science work? But instead, why does it work? And you'll see that this will get us real philosophical real fast. You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. My name is Shalma, and I'm a PhD student at NYU.
And I'm Dan Hooper. I'm a theoretical astrophysicist at Fermilab and at the University of Chicago. So let's start just by talking about what science is. In particular, when we talk about doing science, what we mean is trying to find out something about the world by using this thing we call the scientific method. So Shalma, in high school, you probably were taught some definition of the scientific method, right?
Right, yeah. I feel like it was even earlier. I feel like that's like elementary school science. They're like, oh, okay, you make an observation, then you make a hypothesis, and then you design an experiment to test the hypothesis, and then you have evidence one way or the other.
Yeah, and then some iterative version of this and all that, and you get closer and closer to a theory that produces predictions that agree with observations, right? So we all know, science isn't exactly done this way in the real world, but like in some sort of idealized sense, this is a sort of procedure we're taking when we do something we call science. But what are we really doing? Like, what are we trying to accomplish when we use this method?
So I guess one idea is that there is some actual fundamental way that the universe works, and we're just trying to get at that. So by using the scientific method, we're getting closer and closer to understanding how the world actually works.
So in other words, you think science is a means by which to find out what the universe is really like?
Sure.
Right. Well, that might be true. And a lot of people think it is, but it's not super obvious that that's the only possible interpretation. So let's talk about that today. And to do that, I want to talk about an example that comes from astronomy as it was practiced in the Middle Ages. So here I have in mind, this long period of time from roughly the end of the Roman Empire to the beginning of the Italian Renaissance. So like several hundred-ish years CE to like 1450 CE. At this time in kind of the European academia, or what was coming together as academia, astronomers were in pretty uniform agreement that the Earth was at the center of the universe, not the sun. So it was a geocentric hypothesis or theory. And all the planets, which to them included the sun and the moon, orbited the Earth in perfect circles where these objects just moved in uniform speeds, this constant velocity in these perfect circles. And of course, they were doing astronomy just with the naked eye. There were no telescopes at this point in history. They had astrolabes and other kinds of astronomical instruments, but their eyes were their primary tool for doing observational astronomy. On the one hand, there were a group of people who were thinking about the cosmos, or what we would now think of as a solar system. I'm sure they didn't think of it as a solar system since the sun was just one of the planets. And this group considered themselves to be philosophers, and they were overwhelmingly influenced by the ancient philosopher Aristotle. And they thought that, they had figured out rules about how planets move and, what carried them through the cosmos and why, and what stuff was made of. But they weren't really concerned with any observations, which usually didn't agree with their theories. And they weren't using their theories to make any predictions. So I think it's pretty fair to say that this group of philosophers in the Middle Ages weren't really trying to apply the scientific method to any questions of astronomy. But on the other hand, there was a totally different group. They usually thought of themselves as mathematical astronomers. And they were building on the work of second century philosopher and mathematician named Claudius Ptolemy, Ptolmy. He was affiliated with the Museum of Alexandria in Egypt. And his great claim to fame is being able to build complicated astronomical models that would allow him to make really spectacularly accurate calendars and really useful for things like navigation. In particular, by making these very complicated models, you could predict very accurately where different planets and other objects would be in the sky at any given particular time. And this had all sorts of, useful applications.
So the thing about these pretty successful and useful Ptolemaic theories was that they were really complicated. In order to accurately predict the motion of all the objects in the solar system, you can't just have circular orbits. You have to correct for all the other features of the motion. And they did that by adding things called epicycles. Basically, on top of the circular motion of a planet, they add another circle to make a sort of spiral-like motion that fits the data better.
And sometimes you would put like an epicycle on top of an epicycle on top of an epicycle, however many it would take to improve the agreement with the observations in the night sky.
Ptolemy's theories included lots of other quirks too, things called eccentrics and quants that modeled the orbits of different planets around the Earth, except this time with the Earth slightly off-center and things like that. So the main point here is that Ptolemy and all those who followed him had no reservations of just stuffing their theories with lots of these mathematical tools and details if it meant making a more accurate calendar.
So one of the things I personally find most interesting about the Ptolemaic astronomers is it seems like they overwhelmingly didn't think these things that were in their theories really existed out there in the universe. They didn't think that there were real epicycles or eccentrics or quants. They thought of these features that they included just as mathematical devices, things that would, lead to a better calendar, but not that actually describe something that was actually going on out there in the universe. A modern philosopher would say that they were making an instrumentalist endeavor here. They were just trying to build a useful theory or model, not one that really had anything directly to do with reality. Okay, so now imagine that you were an astronomer in, say, the year 1400 or something. So all of the available data that you're aware of agree really well with the best, most sophisticated Ptolemaic models. If you have enough epicycles, eccentrics, and quants, you can explain everything you can observe in the night sky. In light of that, why would somebody not think that such a model is likely to be true? As a modern scientist, I think that when I have a theory that agrees with all the data I have, then it's pretty likely to be true. But that's not the way they thought about it. And if we go even further, let's say hypothetically, there were a model that made perfect predictions for all possible observations that one could ever conduct. Could somebody still consider a theory like that to be untrue or maybe likely to be untrue? And if so, what are we really relying on to make this determination with? It can't be the scientific method, because the scientific method says if something agrees with the data, you have to elevate its status. And if it agrees with all the data that could ever exist, you can't imagine a better theory than that. Let's move a little bit out of the Middle Ages, when Nicholas Copernicus comes along, and his works were published just as he died in 1543. And he gets the heliocentric thing right. He knows that the sun, or thinks that the sun is at the center of the universe, and that the Earth and the other planets orbit it. But he doesn't get it exactly right. He sticks with uniform circular motion as a principle, as opposed to the elliptical orbits that Kepler would introduce a little while later. And so the predictions this model made weren't all that accurate. So to make up for the, weaknesses of these predictions, Copernicus added epicycles to his theory, and then it worked well, or about as well as the best Ptolemaic models that were available at the time. So you should think of Copernican models and Ptolemaic models kind of competing with each other. Both did about as well as the other in terms of explaining the data that was available at the time. So now ponder this question. Like the Copernican model without any epicycles, the simple version of the Copernican model, would have described approximately reality better than the model that he actually published with the epicycles included. But the one with epicycles agreed with the data more. So is this an example where the scientific method is failing us? Is it pulling us towards theories that describe reality less well? Yeah, what do you think?
So I feel like we've mentioned this before in a previous episode, but I don't remember which. But like, you can tell when a theory is better than another if it describes more with less, right? Or if it predicts more with less, right? So like maybe the Copernican model without epicycles like describes the theory less accurately, but it can describe a lot more with like much less complexity. Like all you need is like the Earth going in circles around the sun rather than like these layers of epicycles or whatever.
Yeah, that makes a lot of sense. We apply this principle known as Occam's razor to a lot of our theories where we say, well, sure, I could fit the data a little bit better with all this extra complicated stuff, but I don't think that's worth it in the end. Or you could find examples where you have a pretty simple theory that explains the data reasonably well or something like this. And you might judge that's a pretty good theory, even if it's not a perfect fit to the data, all that sort of stuff. All right, so if by introducing epicycles, Copernicus could enable his model to make better predictions, and it did, does it make you wonder what features of today's scientific theories might not actually exist? Like, let's say, maybe there's no such thing as an electron, all right? But by treating the universe as if electrons are a thing and following them to their logical consequences, we end up accidentally more or less making better predictions. We would be tricked into thinking electrons are a real feature of our universe, or maybe atoms or Higgs bosons, or who knows, are these things actually out there in the universe? Or is it possible they're just very useful mathematical devices?
So at this point, the challenge I have, I guess, is that Ptolemy and Copernicus can theorize about how the planets move around the solar system and so on, but, eventually we can actually just build a rocket ship and go up into space and just take a look and see how the planets are moving around the sun. And so can't we sort of see electrons and atoms in some analogous way to that?
So I would say for any theory, maybe a theory that electrons exist, there's a long list of predictions that could hypothetically make. Some of those we can test today. Some we could test in principle. Some facets of these objects I don't think we could ever test. But there's always a possibility that this is just a placeholder, a mathematical placeholder for something more deep down true. Here's an example that I really like. So, Isaac Newton conceived of the force of gravity as this thing that pulled masses together, that reached across space and acted at a distance and all this sort of stuff. Einstein taught us that there really isn't a force of gravity. That's just kind of a useful fiction. In fact, space and time are curved in such a way that creates the impression of a force of gravity. And it's very useful to think about gravity as a force. We still teach, physics classes as if gravity is a force because it's a really useful tool. But deep down, there isn't any such thing. So maybe electrons and Higgs bosons and atoms aren't real in this sense, but are super useful as a mathematical construct. So back in episode 13 of this podcast, we talked about different interpretations of quantum mechanics. And some of these interpretations, like the Copenhagen interpretation and the many worlds interpretation, make exactly the same predictions, not just for all the experiments we've done so far, but for all of the experiments we could ever even hypothetically do. They make exactly the same predictions in all conceivable circumstances. So, like, there doesn't seem to be any way to use the scientific method to tell us which of these we should prefer over the other. If we do have a preference, and a lot of us do, I think I do, then we're not using the scientific method to draw the conclusion about what we should prefer. We're using something else, and it's not always clear exactly what that is. So let's say I'm a, many worlds quantum mechanics advocate, and you're a Copernican. I don't mean that. You're a Copenhagen quantum mechanics advocate.
Copernican, just like everything orbits around the nucleus.
So let's say I'm a proponent of many worlds quantum mechanics, and you're a proponent of the Copenhagen interpretation of quantum mechanics. You think that when one makes an observation, the wave function collapses, and that's how the universe really works. I think that when there's observation, you actually just find out which branch of the wave function you're in, and there's no such thing as a wave function collapse. So yeah, we're describing two different realities that both make identical predictions for every kind of observation, experiment, or measurement we could ever hypothetically do.
Mm-hmm. So we've probably talked about this in our quantum interpretation episode, but what is it, if not the scientific method, that actually makes you prefer one interpretation?
When I look at the Copenhagen interpretation, I find it really distasteful for non-empirical or non-scientific reasons that the act of observing, the requirement of some sort of, conscious observer to play a part in dictating how the universe responds to things, that I find just kind of inconceivably implausible. So, I can't describe an experiment that will support that claim. But it's a prejudice, I guess, I carry into my viewing this problem, my reflecting on this problem. And a lot of people agree with me, but some people don't. And it's possible that I'll just never be able to convince those people who disagree. And it's possible they'll never be able to convince me, because we just kind of start from different philosophical outlooks on this sort of question.
Mm-hmm. So it's distaste and your physical intuition that tells you that you prefer one over the other. And when you try to convince other people to agree with you, you probably appeal to those things too.
I think so. I don't think it's quite as subjective as, like, I don't know, my taste in music or something. I think there are, like, reasoned arguments one can make, but they certainly don't reach the level of proof. They're and they don't have the kind of weight that an experimental result would carry with it. It's something else, and it's a little more subtle, and scientists don't like to necessarily rely on non-empirical evidence to convince somebody that one theory is better than another.
Right, and that's why it's kind of been relegated to the philosophy world.
And physicists are still arguing about this today, 100 years after the invention of quantum mechanics, or almost 100 years, or whatever, roughly 100 years.
Okay, so would you say that, like, the fact that we can never know what quantum mechanics means for certain, like with a proof, does that, like, mean that our theories don't describe reality?
Well, there's an ongoing debate among philosophers of science today about whether or not the scientific method really reveals anything about reality at all. Okay. So whether you're talking about quantum mechanics or atoms and electrons or planetary orbits or whatever, they're not in agreement that the way we go about doing the scientific method actually gets us a real answer to the questions we're asking. Most actual scientists, most practicing scientists thinks it does tell them about reality to the extent that they think about these sorts of questions. But it's not as obvious to the philosophers, or to me for that matter. Either way, we know that science is actually working to make us be better able to control our universe. Like we have this incredible technology that comes from applying the scientific method. But how it does that is a lot less clear. So there are kind of two camps in the philosophy of science when it comes to this. And it's oversimplifying it, but we can think about it this way. There are those who consider themselves realists, okay? And there are examples like Wilfrid Sellers and Hilary Putnam and others who consider themselves realists in this perspective. There are a bunch of different definitions, but the one I've found that I like best is by a Canadian philosopher named James Robert Brown, who happens to be my second favorite James Brown, by the way. He describes realism as saying that science aims to give us in its theories a literally true story of what the world is like, and the acceptance of a theory involves the belief that that theory is true. Okay? So, in other words, if you're a realist, you think that what we're trying to do with science is find out what the world really is. And when you say, I think a theory is likely to be true, you think the things that theory described are actually likely to exist. On the other hand, there's a group of philosophers of science who consider themselves to be anti-realists. They would argue that a theory doesn't have to be true in order for it to be a good theory. A good theory will be something that has other positive features, other virtues. One that's commonly talked about is that a theory is empirically adequate or maybe even useful. So after all, Ptolemaic models of the solar system were very useful. They made great calendars, and that made those theories good from a certain standpoint. So from an anti-realist perspective, a modern one anyway, science provides us with a way of acquiring theories that are empirically adequate. They make good predictions that agree with the data. And when we accept a theory, all that means, the only thing it involves is a belief that that theory is empirically adequate, not necessarily that it's literally true. In other words, an anti-realist thinks a theory could be good without having anything necessarily to do with the reality of things in our universe.
So I have one response, which is that when we're talking about, the fact that we don't know which quantum interpretation is true, we can never know that. But we got to quantum mechanics itself as a theory through the scientific method. And if we didn't do that, then we would have no idea that we could even talk about realities being like this, right? So maybe there is, maybe it does get us closer to reality, even if it can't pinpoint it exactly.
Well, everybody doing a philosophy of science, whether they're a realist or anti-realist or something in between or something different, they all agree science teaches us something. No one's denying the utility of science. It teaches us something. It reveals something to us. But whether that something is a literally true description of things in our universe or not, that is a lot more up for debate. So let me talk a little bit about some of the arguments that the realists and anti-realists make to support their position. So probably the most important argument in favor of realism, and it's usually associated with this American philosopher Hilary Putnam, who says that realism is the only explanation that we have that doesn't make the success of science a miracle. So in other words, we have these scientific theories that make all these diverse range of very precise predictions that all turn out to be true. And if they weren't describing something real, at least most of the time, there's no reason, he would argue, that we have any right to expect those theories to have been so successful. It would have been a miracle if some theory that was positive to explain a certain amount of data, and then we have all this other data later that it all disagrees with and all explains. Well, the only reason that you can explain that with is the idea that, in fact, that theory is true, describing real objects, real things, real facets of our universe. On the other hand, the anti-realists can push back. And there are a bunch of different theories. Some of them have to do with kind of Darwinian theories of how scientific theories evolve and stuff. I've never found those theories super compelling. So I'm going to focus on the anti-realist response that I think maybe is the most convincing from my perspective. And that has to do with what they call the underdetermination of theories. So the idea is this. So for any set of data you could ever have, there are some huge number, maybe infinite number of theories that could fit that data. The chance that any particular theory, even if it fits the data really well, the chance that that theory is the right one is vanishingly small because there are some gargantuan or maybe infinite number of choices. So that all fit the data well. So no matter how good your theory has done to describe the tests you've put it through, there are a huge number of other ones that could be contenders as well. And since you can't tell using the scientific method which ones of those are right, you have no right to expect the one you've picked is likely to be true. So we talk about these quantum mechanical theories or interpretations, the Copenhagen or many worlds interpretation. But what these anti-realists would say is like, well, those are just two of them, but there are like maybe thousands or millions or billions of other theories of quantum mechanics that one could write down that would agree with all this data. Probably neither of these two is right. They're a useful theory. They allow us to predict things. They allow us to build cell phones and, the laptop I'm staring into right now. And they allow us to describe any number of facets of our universe. But come on, like the odds that the theory we happen to pick and use as our tool to make these predictions, the odds that one's actually describing reality is basically zero.
To your knowledge, does this like anti-realist camp have a concept of progress?
Yeah, I think an anti-realist would respond to that by saying the goal of science isn't to come up with theories that literally describe reality. That's not what it does. It's not what it's built to do. But that doesn't mean science doesn't progress. It can make theories that describe more observations and more data better. They can become increasingly empirically adequate. And that's powerful. It allows us to build technology. It allows us to control our world. It allows us to do all the things that science has allowed us to do without necessarily saying anything about how the universe really is. I will say that like really serious people at really serious universities who think about this a lot more than I ever will have the luxury of doing, come down on both sides of this. Like, so it is not a settled issue.
Right now, at the end of this recording this episode, I'm personally feeling closer to a realist than I expected myself to. I expected myself to like, because of things like the quantum interpretation issue and stuff, and because like science is at the end of the day this social thing, feel like there is always a gap between what our theories are and what, reality is. But now I feel like our theories can approach what the world is like, but with that gap in mind. I think better theories of physics are getting us closer to an understanding of what the world really is, even if there is like a limit to how good that can get.
Yeah. And I, for one, don't have my mind made up on this issue at all. Like I can wake up one morning and feel very much like in the realist camp. And then later that afternoon, ponder it a little bit and like, no, that anti-realist, underdetermination, argument seems really compelling. And then the next day I'm a realist again. And then, I don't know. I just, this has been a long and winding road for me. And I'm not sure where I stand, but the one thing I'm really sure about is that science works at doing the thing it does. And it makes, life better, both as a practicing scientist and as somebody who benefits from the technology that science creates. So let's keep doing it.
This episode was produced and edited by me, Shalma Wegsman. Research and writing is done by Dan Hooper and I. Dan is a theoretical physicist at Fermilab and the University of Chicago and is the author of many books, including most recently, At the Edge of Time, Exploring the Mysteries of Our Universe's First Seconds. All music in Why This Universe is produced by Jake Kleinbaum. Thank you so much for your support and for listening, and we hope you tune in next time to Why This Universe.